Okay, today we finally come to the heart of the matter, to Einstein's field equation. So this will be at the center of this lecture today. But before coming to Einstein's field equation, I have to finish the section on the rule of minimal coupling. This was the last thing we were doing. I had formulated the rule, very roughly speaking. It says, takes the laws of special relativity, any sort of field equation you like from special relativity, replace the etas by g's, and replace the partial derivatives by covariant derivatives. So then you get the correct general relativistic law. So that's a rule of thumb. And well, it has a great advantage that it is in agreement with the equivalence principle automatically. So you always automatically satisfy the equivalence principle if you do this. Of course, there's not a guarantee that it is a right law of nature which you get in this way. It's a necessary but not a sufficient condition. So as an example, I already briefly treated the electromagnetic field. So that was the last thing we had on the board. So the translation rule for the formulas of electromagnetism from special relativity to general relativity. And now let me do the same thing very quickly for a perfect fluid. So for a perfect fluid, we also discussed what the correct equations are in special relativity. Actually, we did a problem on one of the worksheets for this. In the lecture, I considered the dust case. That's a perfect fluid with vanishing pressure. That's what we call a dust. That's what I considered in the lecture. And then in one of the worksheets, we had a perfect fluid with non-vanishing pressure. So the formulas in special relativity were the following. So the energy momentum tensor was something like, I never know where the C's are, because usually I work with C equal 1. So let me copy this to be sure. Maybe I should use other indices, because now the mass density mu occurs, so it's better to have a different letter here, just to avoid confusion. That's the mass density, and that's the pressure. These are scalar functions. That's the 4 velocity, u rho, u sigma, and then I have plus p eta rho sigma in special relativity. So that's special relativity in inertial coordinates. That's the energy momentum tensor for a perfect fluid. And then we derived on one of the worksheets the Euler equations, the equations of motion, which were mu plus p over c squared, u rho partial rho u sigma plus d tau p, derivative of the pressure, eta tau sigma plus 1 over c squared u tau u sigma, and this is 0. Yeah? So that's a first order differential equation for the 4 velocity. The 4 velocity is a tangent to the curves, so it's a second order equation for the curves, for the flow lines of the fluid. And if the pressure is 0, you see this term is not there, and this is also simpler. And then the equation simply says that this expression must be 0. And that's the equation that the flow lines must be straight lines. That's what we discussed a couple of weeks ago. And now we translate this into general relativity. Oops, relativity. That's hardly readable. Relativity with a rule of minimal coupling. And the rule was, look where the etas are and look where partial derivatives are, and then replace them. Replace the etas with g, and replace the partial derivative with covariant derivatives. So we get an energy momentum tensor for a perfect fluid as u plus pc squared u rho u sigma plus p, and now the metric g rho sigma, space-time metric in arbitrary coordinates. And the Euler equation, the equation of motion for the flow lines of a perfect fluid, becomes this here. Oops, rho sigma. So you see that's a covariant derivative in the direction of u. Yeah? So this tells you how the tangent field u changes if you go along an integral curve of u. Yeah? So if the integral curves would be geodesics, then this would be 0. Yeah, this would be precisely the equation the equation that this is 0, that's precisely the condition that integral curves are geodesics. But in general, they are not geodesics because we have this term here with the pressure. Well, just to use a rule of minimal coupling mechanically, I replace this with a covariant derivative. Actually, I could leave here the partial derivative because when acting on a scalar field, the two things are the same, right? If you remember. If a partial derivative acts on a scalar field, then I can replace it by a covariant derivative and vice versa. So the difference is only relevant if I have tensor fields of higher rank here. But it's certainly not wrong if I write a partial derivative, a covariant derivative here. And the eta becomes a g tau sigma plus 1 over c squared u tau u sigma is 0. So that's the equation of motion for the flow lines of a perfect fluid. So the gradient of the pressure tells us how the flow lines deviate from geodesics, right? If this term is 0, if the pressure is 0 or at least constant, then this term is not there, and we have geodesic flow lines. So then, and also for a dust in particular, that's the case when the pressure is 0, right? For a dust, we just have the geodesic equation, saying that u is parallel along its own integral curves. So the integral curves of u are geodesics. So that's the way in which the rule of minimal coupling works in examples. I should mention that many people use a different notation. I think I have mentioned this a while ago, that instead of using this covariant derivative symbol, they use a semicolon. Yeah, so they would write u sigma and then semicolon rho. And for a partial derivative, they would write comma rho. And then this rule that partial derivatives become covariant derivatives can be expressed by saying change any comma into a semicolon. Yeah? So the rule of minimal coupling is also known as a comma goes to semicolon rule in many books. Yeah? Misner, and Wheeler, for instance, they often use this terminology. But as I don't use this notation with comma and semicolon, it doesn't fit very well to our notation. Okay, so that was the rule of minimal coupling. And two examples, and you can apply this to any example you like. Yeah? So we can apply it, for instance, to the Dirac equation. If you know how the Dirac equation looks in special relativity, then use this rule and you get the Dirac equation on the general relativistic spacetime. And for all the examples I've treated here, actually the rule of minimal coupling gives the correct law. We have discussed last time briefly that there might be ambiguities. For instance, if you have second derivatives here. Yeah, here we have only first derivatives. And then there's no ambiguity. But if I would have a second derivative here, two partial derivatives, one after the other, then the order would matter if I replace them by covariant derivatives, right? And then an ambiguity would arise. So at the special relativistic level, the order is irrelevant because partial derivatives commute. But if I translate this, then all of a sudden the order becomes relevant, yeah? Because covariant derivatives do not commute. And then the matter becomes a bit more tricky, and then you have to be careful. So you shouldn't rely on the rule of minimal coupling blindly. But in many cases, it gives the correct equations. So we will use this, of course, the rule of minimal coupling. We will use it in 20 minutes or so again when we discuss the right-hand side of Einstein's field equation. But for the time being, I leave this section now. So this was about fields on a general relativistic spacetime. And now we come to the question, what's the equation for the gravitational field itself? And that's what we call Einstein's field equation. So this was about fields on a general relativistic spacetime. Yeah, I have a G, a metric G. It comes with a covariant derivative. And now I ask how fields on the spacetime behave. For instance, how this 4 velocity behaves. What differential equation governs the motion of this 4 velocity. Or for a Maxwell field, we ask how the electromagnetic field tensor behaves on the field. Here the gravitational field is, so to speak, the geometric background. Yeah, it's not the dynamical variable. There's no derivative of G. Yeah? There are derivatives of U or of F in the Maxwell's equation. So that's not a dynamical equation for the gravitational field. The dynamical equation for the gravitational field is this here. And that's what we want to discuss now. And that's something new. So we have to start thinking about this from scratch, so to speak. So of course we are guided by Newton's theory. We have a good theory of gravity. That's Newton's theory. And what we want to do should, of course, be not completely unrelated to Newton's theory. Of course, at least in some limiting case, Newton's theory should be reproduced. So let's look at Newton's theory, and let's then discuss how we can generalize this into this setting of general relativity. So in Newton's theory, of gravity, we have some equations, and we want to ask what are the analogs in Einstein's theory. So Newton's theory, we have discussed this several times, consists essentially in two equations. The first is the equation of motion for a particle in a gravitational field. And I could write this in this way. Second derivative with respect to time. In Newton's theory, there's only a universal time. Then the trajectory of the particle in space, and this is equal to the negative gradient. So if I take it to this side, then it is equal to, let me write it with a del sign, del phi. Yeah? That's the equation of motion for a particle. The mass drops out. I have the inertial mass in front of this, and I have the gravitational mass in front of this. An experiment tells that they are equal, so I can cancel the two masses. And then I'm left with this. And the other equation is the Poisson equation. This is 1 over 4 pi g Laplace phi is the mass density mu. Yeah, so if you give me the mass density, if you tell me how masses are distributed here, then this equation tells me what the gravitational field is. Of course, it doesn't tell me uniquely. I also need boundary conditions in order to get a unique solution, right? But it gives me a differential equation for the phi. And now we want to consider the passage from left to right. And you already know what's the analog of this here. So that's the equation of motion for a particle which is influenced by gravity alone. Yeah? So that's also what we call a freely falling particle. Yeah, a particle which is influenced by gravity alone. So in Newton's terminology, the only force acting on this is a gradient of the gravitational potential. So my question, what is the analog in Einstein's theory in general relativity? We have already talked about this. What's the analog of this? What's the equation of motion for a freely falling particle? That's the geodesic equation, yeah. So I can write it in this way, x mu double dot plus gamma mu sigma x mu dot x sigma dot. And the dot now refers to proper time. Yeah? Okay, and this is 0. Yeah, and the question is, what's the analog of this? And that's something we haven't talked about yet. So what's the analog of the Poisson equation? That's what we want to discuss now. Well, looking at the first equation gives us a hint what should be the analog of the phi. Yeah? If we compare these two equations, we see where we had the gradient of phi in Newtonian theory, we now have something with the Christoffel symbols. So apparently the Christoffel symbols are the analog of the gradient of phi. The Christoffel symbols involve first derivatives of the metric. So this would mean that the metric is the analog of the gravitational potential, right? I have a derivative of phi here. I have derivatives of g here. So the metric is probably the analog of the gravitational potential. So the analogy is the following. When I have the 4 on the phi on the left-hand side, I would replace it by the metric g. And the metric g, just to remind you, is something of this sort. If I write it in coordinates, it has 2 indices. And it gives me a tensor field of rank O0. So this is, of course, a mathematically much more complicated object, right? This is just one scalar. This is, well, if I just count the scalar components, how many are these? Can you guess this? So if you write the metric components in a matrix scheme, how many entries do you get? They are in 4 dimensions. 16. So in the yes. So at first sight you would say there are 16 entries, right? That's right. 4 times 4. But are they all independent, or is there a condition on the g's? They are symmetric, right? So how many are left? 8. 10, I would say 10. Yeah? 4 in the diagonal and 6 off the diagonal. The other 6 are then determined by symmetry. So these are 10 scalars. So where we had 1 scalar in Newtonian theory, now we have 10 scalars. So you can already imagine that the analog of the field equation will become more complicated. So then we need an analog of the mu. So what is this? Actually, we have already talked about this when we talked about the heuristic approach to general relativity. I think that was chapter 3 or something like that. Remember, what was the conclusion? What would be the analog of the mass density mu? What would be on the right-hand side of the field equation? What's the source of the gravitational field?
Must be the energy momentum tensor.
Yes, yeah, that was the outcome of our discussion. Because the mass density, well, there are several reasons why it should not be the mass density. The most important one is that in relativity, mass is only one form of energy, can be converted into other forms of energy, right? And we would ask ourselves, why is only this particular form of the energy on the right-hand side of the field equation, and why not all forms of energy? So it would be very natural to expect that this is a T. And also, and of course, this fits very well with the observation that the G has 2 indices, so that we get with the symmetry assumption 10 independent components, because the energy momentum tensor also has 10 independent components. So it's a quantity which fits very well with the idea that on the left-hand side I have something with a metric, and on the right-hand side something with this thing here. So this has also. And in the theory we are discussing here, the standard general relativity, this is also symmetric. Yeah? People who include torsions, they have a more general point of view. They allow for antisymmetric parts of the energy momentum tensor. But the standard Einstein theory works with the symmetric energy momentum tensor. Well, and then what we need is an analog of this differential operator. So here we have 1 over 4pg del. Yeah, this would obviously go into some differential operator. So this would be some differential operator. So if I take this together, so we look for the field equation in the form, well, I just replace anything according to this rule. So on the left-hand side, I have this operator, which is replaced by this d, which I don't know yet. The phi is replaced by the metric, and the energy momentum tensor is replaced by the t. So that would be the general form of the field equation. And now, of course, I have to think about what property should this differential operator satisfy. Actually, when Einstein approached his field theory, which he found in 1915, and which he looked for over almost a decade, he didn't know a very nice theorem, which was proven later. And actually, from our point of view, I think the best approach to Einstein's field equation is using this theorem. It was proven in the 1970s by a person by the name of Lovelock. It's known as the Lovelock theorem. And it tells us that this operator is uniquely determined by 2 properties which are very natural in our context. So let me write these, how do I want to call these, L1 and L2? Yes. Mm-hmm. So we want to assume that D satisfies 2 properties. And of course, we should discuss if you find these properties natural or reasonable. I call them L1 and L2. The first one is D, or let me apply it to the G, dG should contain derivatives of G up to 2nd order only. So I want to have a 2nd order differential equation. You may ask why. well, obvious argument is in Newton's theory. I have something of second order. So the first try would be to work with something of second order also in the general relativity case. And another argument could be that, well, more or less all basic laws of physics you know about are of second order in the relevant quantity. Newton's equations, Maxwell's equation, if you write them in terms of the potential, or I don't know what else, Klein-Gordon equation. So you very often come along equations of second order, and very rarely across equations that are of higher than second order. Well, there are a few in physics, but they are not really of fundamental nature. So I think that's a reasonable working hypothesis that it is of second order. And the second condition is actually more or less mandatory in our approach, because we know that the energy momentum tensor satisfies certain property. So if this equation should hold, then it should be in such a way, then the operator D should be chosen in such a way that these properties come out, so that they are at least not in contradiction to properties of the T we know. And what do we know about the T? Well, it's the energy momentum tensor, and the idea is that it is the energy momentum tensor of all the matter in the universe, because in principle every sort of energy can act as a source of a gravitational field, right? So this is really the energy momentum tensor of everything which contributes to the gravitational field. And then, of course, it is a closed system, right? So there are no forces in addition to the ones which are covered by these terms here, which are acting on this matter. So that's a closed system. In general, in special relativity, this would mean that the partial derivative and then contracted over two indices should be zero. And with the rule of minimal coupling, this becomes a covariant derivative. So we get in the condition that what is called the covariant derivative of T should be zero. If we want to have this conservation law, the fact that that the energy of the total system is conserved in the sense I've said. And if we require this, then this gives a condition on this operator. So first of all, it should obviously map the G into a second-rank tensor. So dG should be in TO2M for all metric tensors G, and it should satisfy this equation. So the dG should become the energy momentum tensor, and the energy momentum tensor has two indices, right? And it satisfies with the rule of minimal coupling this conservation law if it is a closed system. So this should be satisfied. So that's, well, for consistency reasons, that's almost mandatory that we should have this condition. Yeah, you remember we have talked about energy momentum tensors in special relativity. There we had this equation with a partial derivative. And now I use, of course, the rule of minimal coupling. I replace it by a covariant derivative. Then it becomes this condition. And this gives a condition on the differential operator D, of course. And now the surprising thing is that these two properties fix the operator D uniquely. So you can write down the most general form of the operator D which satisfies these two properties. And that was what Lovelock found out in 1972. So let me just state this theorem. It's a fairly complicated matter to prove this, so I will not prove it here. I just state it, and we will discuss it a little bit. So that's a theorem. It was proven by David Lovelock in 1972. I can give you the precise reference if you like it. It's in Journal of Mathematical Physics, a two-part article. And the statement is D satisfies L1 and L2 if and only if it is of the following form. dg, which is something which has two indices, right? It's a tensor field of second rank. So the components of this are something like dg with indices mu nu. And the claim is it must be this here. There's a constant, which is traditionally called 1 over kappa. Then I have r mu nu, that's a Ricci tensor, minus r half, r is a Ricci scalar, g mu nu plus lambda g mu nu. So where r mu by the way, you will fairly often you will read that people say the field equations with a plural, and some people say field equation, singular, when they talk about Einstein's field equation. And the difference is in the fact that some people think in coordinates, and they say, well, these are, as we have just counted, these are 10 independent equations, right? There's 10 independent components if I write them as scalar equations. So that's the reason for the plural. It's not one equation, it's 10 equations, 10 scalar equations, right? And other people think of the coordinate-free notation. They write it in this way as an equation between tensor fields, and then of course it's just one equation. It's one equation for a tensor field, right? And it's 10 equations for the components of the tensor fields. That's the reason why sometimes you have an S here. By contrast, Maxwell's equations should always have an S, because even if you write them in invariant form, they are two equations, right? So, but Einstein equation is just one if you write it in invariant form. So the field equation reads, let me write it again. So usually you just put the kappa to the other side, and then you are left with r mu nu minus r half g mu nu plus lambda g mu nu is kappa t mu nu. So it involves two constants, kappa and tau. Kappa obviously plays the same role as g played in the Newtonian theory, right? We had 1 over 4 pi g Laplacian replaced by d. And d comes with the 1 over kappa. So you see the g corresponds to the kappa. G is Newton's gravitational constant, and that's another gravitational constant, and for obvious reason it is called Einstein's gravitational constant. So we will discuss later how it is related to the g. Of course, there must be a relation because Newton's theory should come out in a certain limit from Einstein's field equation. So it's called Einstein's gravitational constant. Lambda is called the cosmological constant. And the reason is that we now assume, and we have actually good reason to assume, that it plays a role only in the cosmological context. Namely, if I'm interested only in considerations on a local scale, say in the solar system or even in our galaxy, then the lambda probably can be set equal to 0 without doing an essential mistake. And the reason is that, as we will see in a while, that the Newtonian limit, the Newtonian theory, comes out as a limit of Einstein's theory only with lambda equals 0. So if lambda would be non-zero, then we would have a deviation already from the Newtonian theory at the level where the Newtonian theory is a valid approximation. And as we haven't seen any violation of this sort until now, this gives an argument that in all this situation, where Newtonian theory is a good approximation, the lambda should be negligibly small. But of course, at the cosmological scale, we have to expect that, that the lambda cannot be neglected, and more or less all modern cosmological theory work with some sort of a lambda, where the lambda is not assumed to be 0. So the lambda was introduced by Einstein not over the Lovelock theorem, right? The Lovelock theorem gives a good argument that the lambda should be there. So if you start from Lovelock's theorem, you would ask, why should I set lambda equal to 0? Einstein worked in a different way. He put together the equation with heuristic ideas. And then the question was, why should I introduce a lambda? Yeah? So he filled it in by hand, only in the second step. So in 1915, he had the field equation in this form. And then he found that this equation has no static cosmological solutions. Yeah, solutions where the universe stays as it is for all times. And then he introduced this term by hand in order to produce static solutions. Later, cosmic expansion was observed. Here's the Hubble law. And then Einstein one says that Einstein, well, actually George Gamow says this. So George Gamow reports that in a conversation with Einstein, Einstein said to him that introducing the lambda was the biggest blunder in his life. That's what apparently Einstein said in, I don't know, in the 1940s or something like that. So I think most modern cosmologists would not agree with this point of view. They think that the lambda is there and that it is relevant for cosmology. But it is certainly negligible at a local level. So when we talk about Einstein's field equation, we should always be careful, or if you hear somebody talking about Einstein's field equation, we should be very careful to make sure, does he mean it with a cosmological constant or without the cosmological constant? Yeah, that's a difference. And the other important thing is, yeah, with which energy momentum tensor? So if somebody says, I found a solution to Einstein's field equation, this statement simply doesn't make sense unless he says for which energy momentum tensor. Yeah? You could say every metric is a solution to Einstein's field equation as long as you haven't specified the energy momentum tensor. Give me any metric. Write down G mu news. Yeah, a scheme of G mu news as function of the coordinates. Whatever you like, with sine and cosine and hyperelliptic functions or whatever you like. Then calculate the left-hand side and say this is the energy momentum tensor. And then I have a solution to the equation. That's of course not what is of any physical value, right? It doesn't tell you anything about nature. So the right thing to do is start with this. Tell me what sort of solution you want to find. So for which sort of matter you want to find a solution. This means you specify this term first. And then you try to find a solution. And then you really have to solve a second order differential equation, right? So this involves second derivative of the metric. This involves second derivatives of the metric. So that's a second order nonlinear partial differential equation for the metric. And if you have something here, even if you have 0 here, this is a very difficult, very complicated equation. Actually, the one with a 0 is even more complicated than with some other terms. So the important question is when we speak about Einstein's field equation, for which energy momentum tensor do we discuss this? And I want to mention 3 important cases. I think the most important cases. So the most relevant T mu nu are the following. Relevant in view of astrophysical applications. Yeah, so if you write something here which has absolutely no relation to I don't know, to stars or to the matter distributed on a cosmological scale, then you would say it's not a reasonable physical solution. So it should be something which has some relevance for objects which really exist in the universe. And the first example, which obviously is of relevance, is vacuum. Yeah, vacuum means energy momentum tensor is 0. There's no source. What would you think? For which object would this be a reasonable assumption? So something which exists in nature, which is of relevance, for which we want to use the theory, and where we have the 0 on the right-hand side of Einstein's field equation. Could you think of a physical situation where this is relevant? Think of a star. It's certainly not a good idea to use this for the interior of the star. So you have some matter, yeah, which should be described by a non-vanishing energy momentum tensor. But the exterior of the star, there's no matter. Yeah? If you want to describe the space which surrounds the star, so you have vacuum to a very, very good approximation. Yeah? So that's actually the most important example to which this applies, the exterior of a star. If in the simplest case you assume that it is spherically symmetric, and when you try to work out this problem, then you end up with a Schwarzschild solution. That's the one which we will discuss in the next 2 weeks, yeah, at length. So that's the exterior of a spherically symmetric static object. That's what is described by the Schwarzschild solution. That's a vacuum solution. because it does not apply to the interior of the star. That's another solution, a so-called interior Schwarzschild solution. But it applies to the exterior, where I have vacuum, to a very good approximation. Not precisely, of course, but to a very good approximation. So the vacuum field equation looks like that. R mu nu. So if I do it with a cosmological constant, which for a star or so, of course, we would not do. So we would set this equal to 0. Then we have the 0. And now this can be simplified, actually. This equation can be simplified if we multiply it with g mu nu, with a summation over mu and nu. Then we get here the curvature scalar, right? R mu nu times g mu nu is a curvature scalar. Then we get here R half. Now g mu nu times g mu nu, what is this? 4. Yeah, it's a trace of the Kronecker, right? G mu nu, G mu sigma would be Kronecker sigma mu. And then if I equate these two indices again, then I have the trace of the unit of the Kronecker matrix, if you like to call it this way. Yeah, and this is just the number of dimensions. So this is a 4, and here's the same thing. There's lambda times 4 is 0, so we can solve this for r. This gives a minus 2. With this term together, it gives a minus 1, so I take this to the other side. Then I get r is 4 lambda. So I can replace the r by this here. And then I get r mu nu is what? This is 2 lambda with a minus sign plus 1 lambda. So it is minus lambda. And if I take this to the other side, I have lambda g mu nu. Yeah? So that's the vacuum field equation with a cosmological constant. And if you have it without cosmological constant, it just says Ricci equals 0. That's the vacuum field equation. So because these metrics which satisfy this equation come out of Einstein's theory, metric tensors which satisfy these are called Einstein spaces or Einstein manifolds. Yeah, pseudo-Riemannian manifold where the metric tensor satisfies this here is called an Einstein space or an Einstein manifold. So that's the case when the Ricci tensor is just a scalar multiple of the metric tensor. And by forming the trace, we found that this must be a constant. Lambda must be a constant, cannot depend on the space-time point. So that's the vacuum field equation. So as I said, for lambda equals 0, we will discuss the most famous non-trivial solution of this equation very soon. This will be the Schwarzschild solution. But there's another one, somewhat trivial, another metric which obviously satisfies this equation with lambda equals 0. That's, of course, a space-time of special relativity. Yeah? That's the case where we have g mu nu equal to eta mu nu in an appropriate local chart. That's what we call Minkowski spacetime. Yeah? The spacetime of special relativity is also called Minkowski spacetime because the eta is a Minkowski metric. And that's, of course, a solution of this equation with lambda equals 0. Yeah? Because even the curvature tensor is 0 in this case. So all the more is a contraction of it. So that's a trivial solution. And then I mentioned one non-trivial, that's the Schwarzschild solution, which we will discuss. And there are a number of other solutions, of other famous solutions. Let me just give you a few names, if you have come across them, or if you will come across them, and you might remember. So let me write a few examples, just the names that you have heard them once. Examples of solutions with lambda equals 0. Yeah? Vacuum field equation with vanishing cosmological constant, meaning Ricci tensor is equal to 0. The first one, the trivial, is the Minkowski metric. Well, that has nothing to do with the gravitational field. Yeah, it's just the case, the situation that we have no gravitational field, then of course we should have a solution of the vacuum equation. Minkowski metric, let me write it in this way. Yeah, so in a certain chart you can write it in this way. And obviously then the curvature tensor is 0 and the contraction of the curvature tensor is again 0. Then there's a, so this is space-time of special relativity. Situation when gravity can be neglected. Gravitational field is not considered. The second is a Schwarzschild. Yeah, metric or Schwarzschild solution. And we will discuss this at some length in the next chapter. And this is the space-time outside of a spherical mass. Spherical means in particular non-rotating, right? If it would rotate, then yeah, the rotation axis would break the spherical symmetry. Yeah? So the whole thing should really be completely spherically symmetric. So then it cannot rotate. So it's a non-rotating mass. And a particularly important example is a black hole, a non-rotating black hole. Spherical mass or a non-rotating black hole. So it depends on how far this metric extends. Yeah? If it just extends up to a finite value r, which gives the radius of your star, then it has something to do with the space-time outside of a regular body. And if it is maximally extended, if it goes down as far as possible, then we find the horizon, and then it describes the black hole. So we will discuss this in some detail. Then I mentioned one more metric, which I will not discuss here in this course. It's the so-called Kerr metric, named after Roy Kerr, New Zealander who found this in the 1960s. This is space-time of a rotating black hole. Rotating. Which is much more complicated than the Schwarzschild metric. So I will not have a chance to discuss this here. That would be something for a specialized lecture. Yeah, 2 weeks ago we had Reinhard Meinl here, right? I think some of you have been to his colloquium talk. And actually he is one of the persons who had found a very, very interesting solution to Einstein's field equation with the 0 here on the right-hand side. Together with Gernot Neugebauer, he found 20 years ago or so a solution which describes a space-time outside of a rigidly rotating disk of dust. Here you have a disk, something two-dimensional. It rotates rigidly, and the space-time outside of this, around this disk, can be written explicitly in terms of hyperelliptic function, and that was what they found. So let me write the Neugebauer Meinl space-time or metric. So this is the space-time outside of a rigidly rotating disk of dust. So it could serve as a rough model for a galaxy, right? You could idealize a galaxy as a two-dimensional disk, as something completely flattened which rotates rigidly. But it's not a very subtle model, but it is at least a rough model for a galaxy. And then there are other solutions which I mention only without going into detail, which describe gravitational waves. So we will talk about gravitational waves a little bit after we have talked about the Schwarzschild metric. So we will see that Einstein's field equation with a 0 here has wave-like solutions. And well, I will actually not work out exact solutions, but I will discuss the linearized So the approximative solutions in some detail, not very much detail, but a little bit. And there are also spacetimes which solve these equations exactly. So they are exact wave-like solutions, which were found actually already fairly early in the 1920s. Brinkmann was the first who found solutions of this sort. So all this would be vacuum, right? So the relevant part of spacetime where these solutions apply to, this is a spacetime where I have no matter, where the sources are not situated. The sources are somewhere else, right? Here in this case, for the Schwarzschild metric, the sources are in the interior of the star. But this metric applies to the exterior. So that's vacuum. First important example for an energy momentum tensor. Second example is a perfect fluid. That's a model which is very often used in general relativity. So then the field equation is the following: R mu nu minus R half G mu nu plus lambda G mu nu is the energy momentum tensor of a perfect fluid. We had it on the board. I have it erased. So what was it? Mu plus P over C squared? I think so. Yes, P over C squared. U mu nu, that's the force velocity, that's the mass density, that's the pressure. And then plus P G mu nu. So that's the equation. So you see you have, at first sight you might say, well, this looks more complicated than the vacuum case, right? The vacuum case looks so simple. It's such a short equation, looks so nice. But actually this equation is easier to solve than this here. Why is it so? Because now you have additional parameters, additional functions, the mu and the p and the force velocity to play around with. So you have more functions with which you can play around, right? And that's the reason why it's more likely that you will be able to find a solution. Actually, finding solutions to the vacuum equations is the most difficult task in general relativity. Yeah? Because there you have no functions, no free functions to play around with, like the mu here and the p and the force velocity. So that's a perfect fluid. And actually also in this case, quite a lot of solutions are known. So known or examples, let me say. Examples of solutions. Let me begin with lambda equals 0. But I should remind you, if the P is 0, then we call it a dust. Yeah? Perfect fluid. Maybe I should write this somewhere. So P equals 0, we call it a dust. And actually, a couple of the interesting solutions are dust solutions. And some of them are solutions with pressure. So examples of solutions with lambda equals 0 are the interior Schwarzschild metric. So that was a solution which was also found by Karl Schwarzschild very briefly after he had found the solution for the exterior. So that would be a metric which describes the interior of a star. Yeah? So that describes interior of a static star. And actually, Schwarzschild made the additional assumption that the mu is constant. So that's what he called an incompressible fluid, a static star with mu equal constant. I will talk briefly about the interior Schwarzschild metric. I will not discuss it in detail, but I will make a few remarks after we have discussed the exterior Schwarzschild solution. So I will come back to this. Other ones are the so-called, this was a metric with Oppenheimer and Snyder worked with. So Oppenheimer, that's the American physicist, who is most famous for his role in the Manhattan Project. Yeah, he was the scientific head of the Manhattan Project of building the atomic bombs in the 1940s. But he was a theoretical physicist who worked in various fields, mostly in quantum theory, but he also wrote a couple of papers on general relativity. And together with his student Snyder, he wrote an interesting paper on a ball of dust. So here you need a pressure. If you want to have a static star, you would need a pressure. Now let's assume it is a dust. There's no pressure. What will happen? Of course, the whole thing will collapse, right? It cannot be static. It will collapse. And that's what these two people calculated. So they calculated the collapse of a dust ball. So it describes, this was in the 1930s. Collapse of a ball of dust. So it's a solution of this equation with lambda equals 0 and p equals 0. So it belongs in this section. Where there are other ones, but I think I will mention no other ones with lambda equals 0. But I want to mention some with lambda non-zero, so where we have cosmological solutions. So where we have this, which becomes relevant if we are in a cosmological constants, in a cosmological context. So the most famous are the so-called Friedmann solutions. If I have time enough, and at the end of this course, I will briefly talk about them. So these are cosmological solutions. Describe cosmological models of the whole universe. Yeah? So this here is a good model for a space-time, in a very limited region. Yeah? It just describes a star or a sun, for instance. So this has nothing to do with the model of our universe as a whole. It just describes one gravitating body. It's the same here and also there for the first ones. But this aims at describing our whole universe in a simplified or idealized manner. And the first who found interesting solutions was Alexander Friedmann, Russian mathematician, who in the 1920s established what's nowadays called the Friedmann solution. And they are perfect fluid solutions with a cosmological constant. Another one, maybe you have heard this. It involves a very famous person, namely Kurt Gödel. I'm sure you've heard about Kurt Gödel, the famous mathematician, Austrian mathematician. He was a friend of Einstein. They lived together in Princeton. They used to walk to the university together. So they knew each other very well. And when Einstein turned 70 in 1949, Gödel had a particular gift for him. Not a bottle of wine or something like that, but a solution to his field equation, which is a very nice birthday present, right? So that's what is called the Gödel metric or the Gödel space-time. And this is, again, a dust solution with a cosmological constant. So that's a Gödel metric. So if you would ever come across this, then you know that it belongs into this section. So this is a dust solution with cosmological constant. It's probably not a realistic model for any part of our universe. It has rather pathological properties. So in particular, it has what is called closed time-like lines. So there are world lines. You can move at subluminal velocity along these world lines, and you come back into your own past. So that's the thing which we have discussed in context of special relativity, that you can kill your father before you were born and things like that, right? If you can travel into your own past. And at the general relativistic level, this happens for instance, in this Gödel space-time. And that's the reason why most people say it's not a realistic model of our universe. But it's, nonetheless, it is didactically maybe quite interesting just to see what sort of pathologies Einstein's equation allows, right? So these would be examples for perfect fluid solutions. So the realistic ones are models of stars and models of the universe as a whole, right? So here, in the case of the Friedmann solutions, one would say the dust or the perfect fluid model, the perfect fluid, is made up of the galaxies, yeah? Or even of the galaxy clusters. So the particles in the dust are the galaxies, or even the galaxy clusters. Yeah, so that's the idea when you use continuum models for describing the universe as a whole. Okay, so this was perfect fluid. And the third example of an energy momentum tensor I want to mention is the electromagnetic field. And here I consider only the case that the electromagnetic field has no sources and that it is not in a medium. That's what is usually called electrovacuum. Yeah? So it means it is vacuum apart from an electromagnetic field. Yeah, so the only thing which we have on the right-hand side of the field equation is an electromagnetic field without sources, without a medium. So in this case, the Einstein field equation would be this here. Left-hand side this here. And on the right-hand side, we have the energy momentum tensor of a pure electromagnetic field without sources. That's what we had on the board last Friday, I think. There's mu naught, that is permeability of vacuum. Yeah, we have epsilon naught and mu naught in the Maxwell equations. And then we have F, what are the indices, mu and nu? Mu alpha, mu alpha minus 1 over 4, G mu nu, F alpha beta, F alpha beta. F is the electromagnetic field. So that would be electrovacuum. So the source of the gravitational field is an electromagnetic field, right? Electromagnetic field has energy. And the philosophy is that everything that has energy acts as a source for the gravitational field. It is different from Newtonian theory. In Newtonian theory, only the mass density is the source of the gravitational field. In Einstein theory, any sort of energy produces a gravitational field. Because, mass doesn't play a particular role in comparison to other forms of energy. So examples of solutions are the following. So fairly, one which is treated in more or less any book on general relativity, although it is not a particular realistic solution, is the so-called Reissner-Nordström solution, or Reissner-Nordström metric. So that's the solution of this equation. So we have vacuum and an electromagnetic field. So that would be the case, for instance, in the exterior of a charged object. And that's what it describes here, right? If a star is uncharged, then there's pure vacuum outside, nothing. But if it is charged, then there would be an electromagnetic field outside. And that's something which would be described by this equation. So this describes a spherically, or space-time outside of space-time outside of charged spherical static mass. So it's realistic, it's astrophysically not particularly important because all celestial bodies, stars and planets and whatever, have a net charge very, very close to zero. Yeah? So this is the charge of stars or other celestial bodies can usually be neglected. So it's more of academic interest, but nonetheless it is something which you can study as an application of Einstein's field equation. And then there are solutions, wave-like solutions. And now because we have a gravitational field, which is coded into this geometry, and an electromagnetic field, we can have electromagnetic and gravitational waves having interact with each other. And there are solutions of this sort. So there are solutions describing interacting electromagnetic and gravitational waves. So there are whole books about these waves. Typically they are plane waves. They are plane electromagnetic wave, which has energy, which produces a gravitational field. And because the energy propagates in a wave fashion, then also the gravitational field would have a wave-like nature. So these solutions with the wave-like property of these equations have also been studied in great detail. Of course, there's no superposition principle, right? Because Einstein's field equation is nonlinear. So the theory of waves is much more complicated than for pure electromagnetic waves. Yeah? This is linear. Maxwell's equations are linear. But here the left-hand side is nonlinear in the metric. Yeah? There are terms which involve products of the metric. So it's a nonlinear equation. This means the superposition principle doesn't hold. So we cannot do Fourier expansion or things like that, which is quite common for other types of waves. So these gravitational waves coupled to electromagnetic waves or to whatever, they are much, much more complicated than other waves. So this gives you just an idea. It was meant as just giving you a rough idea of what sort of solutions are known and what sort of solutions are sought for. And whereas there's a fairly large community which produces solutions after solutions, which well, most of them have absolutely no relation to physics. Yeah? So they are just mathematical solutions. Whereas the journals which publish papers on general relativity, they always have the problem that they get papers where somebody says, I have found a new solution. And then the referees discuss, is this really relevant or is it not relevant? Yeah? So there are so many solutions which can be constructed mathematically. And the difficult thing is to find out those which are really physically relevant. So the ones I've mentioned here have, at least to some extent, certainly physical relevant. So the most important ones are Schwarzschild, static space-time outside of a spherically symmetric star. But also the Friedmann solutions are very, very important. And maybe these wave-like solutions, they are also relevant. Okay, so now I have 20 minutes. So I want to add a few more remarks on Einstein's field equation before we then turn to the first solution. Yes, let me make 3 remarks. I squeeze them here. Oops. So the first remark is maybe it is good to know that Einstein's field equation can be derived from a variational principle. I will not work with a variational principle here, but it's often used in the literature. And for the investigation of properties of metric, it's really helpful for many aspects. But I will not use it here, so I just make a quick remark. Einstein's field equation can be derived from a variational principle. And the variational principle, well, it's, as usual, it's symbolically written in this way. So the variation of a certain W vanishes. And of course, this doesn't tell you much as long as you don't know what the W is. And the W is a so-called Einstein-Hilbert action. That's the action which gives the field equation as a solution. So this is an integral over a space-time domain omega. And then I have r half minus, right, with my choice of, and here I have a Lagrange function which has an index MAT, which stands for matter. And then comes the volume element. That's the determinant of the metric under the square root. And then dx naught, yes, I've written it in this way. dx1, that's not enough space. Let me write it a little bit smaller. dx1, dx2, dx3. So what is this? So where omega is a space-time region, Yeah? Something which is coordinatized by the 4 coordinates. So it's a domain, not in space, but in space-time. R, of course, is a Ricci scalar. This here is the meta-Lagrange function, or Lagrangian, as it is often said in English. Well, what is this? What has this to do with the energy momentum tensor? In the field equation, in the differential equation version, we have the energy momentum tensor. So obviously this must have something to do with the energy momentum tensor. And the relation is that I get this if I differentiate this with respect to the metric. Yeah, let me write it this way. Yeah, so this is something which involves the matter fields and the metric. And if I take the derivative with respect to the metric, then I get the energy momentum tensor. So if you write down the Euler-Lagrange equations for this action, then of course these derivatives will occur, right? And that's how the energy momentum tensor comes into the game. Should I explain something more? Yeah, the delta. The delta is a variation keeping metric on the boundary of omega fixed. Yeah? So when I vary, when I calculate a variation, this means that I change the function. Here the g is a relevant function, so I modify the g a little bit, and then I try to find out those metrics for which this variation becomes 0. And this is done with keeping the values on the boundary fixed. So it's analogous to what you do with curves. For the geodesic equation, for instance, there you keep the endpoints fixed, right? So you're on a one-dimensional interval, a parameter interval, and you keep the endpoints fixed. And here you have a four-dimensional region, so it has a whole boundary, and you keep the value on the boundary fixed. And if you do this, if you just apply the variational machinery with these interpretation, then you reproduce Einstein's field equation. Without a cosmological constant. I have no cosmological constant here. So delta W reproduces, or is equivalent to Einstein's field equation without cosmological constant. Actually, it was not Einstein who found this out. It was David Hilbert. He was German. David Hilbert. He did this partly independent of Einstein. And there is some debate, there was a fairly fiery debate between Einstein and Hilbert about priorities. Because Hilbert had this variational problem a little bit earlier, before Einstein had this differential equation. So when some people ask, is it really justified to call it Einstein's field equation? Should it not be called Hilbert's field equation or Einstein-Hilbert field equation? But I think if you check the historical background carefully, you will observe two things. First of all, Hilbert did not work independent of Einstein. Einstein gave a talk in Göttingen where he presented his result, and Hilbert built upon this. So he was not independent of Einstein. And where the whole physical ideas, the whole physical setup, the very ideas of general relativity are definitely Einstein's. There can be no doubt about this. So what Hilbert could be credited for, and should be credited for, is that he was the first who found a variational principle for the field equation. That's certainly what he did first. And it's certainly justified to call this not the Einstein action, but rather the Einstein-Hilbert action. And that's what is usually done. Yeah? So this variational principle, this action functional here, this is known as Einstein-Hilbert action, and that's certainly justified. Can I squeeze this here? So W is called, Einstein-Hilbert action. So this was in 1915 that Hilbert found this. Okay, this was the first remark. So just that you know there is a variational principle. I will not do anything with it. And the other two remarks are about these other two principles which I had mentioned a while ago. When we talked about the heuristic approach to general relativity, we discussed at length the equivalence principle. And I hope I have made clear in what came after that the equivalence principle really is the cornerstone of general relativity. So if the equivalence principle would not hold, then general relativity would certainly have to be modified very strongly. So this would be a serious challenge for general relativity. I'm not saying that it's impossible to remedy the situation, but whenever there is a violation of the equivalence principle actually observed, then general relativity must be modified. Yeah. Then there were these other two principles which played an important role in Einstein's own thinking. So if you read Einstein's original papers or his popular writings, you will come across them all the time. But from nowadays perspective, I think most people would agree that they are not quite so important. So these other two principles do certainly not have the same status as the equivalence principle. And in my view, one could even do without them. So they are of interest actually more or less only for historic reasons. This is a principle of general relativity, as Einstein called it, allgemeines Äquivalenzprinzip, and Mach's principle, which was named so by Einstein because it refers to some ideas of the Viennese physicist and philosopher Ernst Mach. And I had mentioned them briefly when we talked about the heuristic approach to general relativity. And now, as we have the formalism, I should make a remark to what extent they are actually realized in general relativity. So the second remark is, what about the principle of general relativity? Well, this was a principle which says that there are no distinguished coordinate systems. Yeah? That all coordinate systems have equal rights. In special relativity, that's not true. In special relativity, we have these inertial coordinates. And we have written down all our equations in these coordinates, in these distinguished coordinates. If you write them in arbitrary curvilinear coordinates, the equations look different. Yeah, so in special relativity, definitely there are distinguished coordinates. But in general relativity, there are no distinguished coordinates. If you look at Einstein's field equation, it takes the same form in any coordinate system. And so that's what Einstein meant when he talked about the allgemeines Relativitätsprinzip, that the equations should be such that they hold in any coordinate system. And that's realized in general relativity. So Einstein's field equation takes the same form let me write it again just to remind ourselves. Minus r half g mu nu, and if you like, you could also have the cosmological term. This form, this holds in an arbitrary coordinate system. Yeah? If you write it in coordinates x0 to x3, and somebody else now makes a coordinate transformation to new coordinates, x0 twiddle to x3 twiddle, then the same equation holds just with the twiddled expressions. Yeah? So the form is precisely the same thing. So Einstein's field equation takes the same form in all coordinate systems. And if that's your favorite formulation of the principle of general relativity, then one could say that the principle of general relativity is satisfied. So in this sense, that's what we had in section 3, I think this was, where we briefly mentioned this. So in this sense, the principle of general relativity we call, what was it? Yes, it was chapter 3. Is satisfied. some people say that's actually not a deep, a deep observation, because, well, it's certainly true that in special relativity there are distinguished coordinates. I just said this, the inertial coordinates. But if I like, I can write every equation of special relativity in arbitrary coordinates, in curvilinear coordinates. Then the equations look more complicated, but they are valid all the same. So if I insist on writing everything in a way that it holds in any coordinate system, I could do this also in special relativity. And that's the reason why people say, well, that's actually not a very important observation. So it certainly has not the same status as the equivalence principle. In Einstein's own thinking, it was very important. So he was strongly guided by the idea that one should have a formalism which holds in any coordinate system. But from hindsight, it's not considered to be so fundamental. And the other one was Mach's principle. Mach's principle, roughly speaking, says that if I know the distribution of the matter in the universe, then the motion of all freely falling particles should be fixed by this. So the idea is the way in which a particle moves. If I throw this into the space-time and see how it moves, then the way in which it moves is determined by the distribution of all the matter in the universe, not by something else like boundary conditions or things like that. It's determined by the motion by the distribution of the matter. So it's a sort of relative mechanics which is behind this idea. And Ernst Mach was the most violent proponent of a relative mechanics. That mechanics should be formulated only as relative relation between bodies, not as something moving in an absolute sense. And that's the reason why Einstein used the name Mach's principle for this, because it refers to these ideas which are very close to Mach's thinking. Mach himself never formulated this principle. And now let's see how is this satisfied in the field equation. So if I know the mass distribution, well, we would translate this into the energy momentum tensor, right? This is a general relativistic quantity which tells us how the mass is distributed. Does this really tell us how test bodies move in the space-time? So if I know this, somebody gives me this quantity, can I then calculate how a body moves in the space-time? What do you think? What would I need to know if I want to calculate how a particle moves? I'm sorry? Yes, if I would know the metric, then I could calculate this. Then, because from the metric I could calculate the gammas, and the gammas would give me the geodesic equation. But does the right-hand side of the field equation determine the metric? No. No, it's a differential equation, right? It has several solutions for the same source. So without boundary conditions, I wouldn't get a unique solution. Yeah? So I cannot do it without boundary conditions. So in this sense, Mach's principle is not satisfied. So if it was a goal of the whole approach to produce something where Mach's theory is satisfied, then one would say Einstein has failed in this particular respect. But of course, nonetheless, the theory is a very good theory, and most people don't care about Mach's principle. So let me write this down. The mass distribution and this means the energy momentum tensor, right, does not determine the metric and thus the Christoffel symbols. Uniquely. Yeah? I need boundary conditions if I want to get a unique solution to these differential equations. So boundary conditions are needed. So if we have the idea that the motion of particles should be determined by the mass distribution, then this is not satisfied. So Mach's principle and again, this is something which we had in chapter 3. is not satisfied. Well, there are some people, actually several people, who try to salvage this in a way, who say, well, maybe one can formulate mass principle in a slightly different way, and maybe then it is satisfied. And there are still big conferences about the validity of mass principle. A while ago, a couple of years ago, there was such a conference here in Germany where people, I wasn't there, but people told me that it was highly controversial. So what sort of interpretation with mass principle could be associated. So this is a matter of debate still about among people who are interested in this particular aspect. But I think most people working in general relativity don't care about mass principle much. So they are satisfied with the field equation. They know what to, at least in principle, what to do with it. And if mass principle is satisfied or not is not considered a very, very important issue. So these two principles, mass principle and the principle of general relativity, in my view, are mostly of interest for historical reasons. So they are not really fundamental issues of general relativity, but the equivalence principle is. The equivalence principle is the essential cornerstone of general relativity. Okay, so then the last thing we have to do in this section 5 is to discuss the Newtonian limit. This will relate us the constant kappa to the constant g. Yeah, that's still an open question. We have to do this. We will do this tomorrow. It will take, 45 minutes or so. And then we will start working with Schwarzschild solution, which will keep us busy for a while. Okay, see you then.